Okay, so my goal in this video is to show you why when you multiply complex numbers in trig form, you can multiply the r values and add the angles. One little disclaimer before I get into this is you do need to know these identities in order to understand this. This identity, or these angle sum identities, hopefully were introduced in a prior unit in your pre-calculus class. But in any case, let me show you why it's so convenient to multiply complex numbers when they are in their trig form. The other thing notice is that what I have here are cis. That's an abbreviation of what you see above, nothing more. So CIS is just cosine, I is the imaginary number, and S is sine. So remember that a complex number is a two-dimensional number. It has a real part and an imaginary part. So let's just imagine this pink complex number here is has a real part A and imaginary part B. So I could call it A plus BI. And why don't we similarly do something over here for this new complex number? Let's call this C plus DI, right? So let's say we wanted to multiply those two complex numbers. So this is what it would look like. A plus BI times C plus DI, right? So multiplying in this way hopefully is familiar to you. Let's just go over here and do it quickly in like a 2x2 box. So I've got A, BI, C, DI. So when you multiply these two, you get AC. A times DI is ADI. BI times C is BCI. And BI times DI, since I squared is -1, you get negative BD. Okay, so what I have here, and I'm circling, that's going to be the real part of the answer. And remember, a complex number has a real and imaginary part. So it's going to be AC. So it's going to equal AC minus BD. It's the real part. Plus, and the imaginary part is this. So let's write that as AD plus BC. BC with let's put the I out here. Okay, that's the imaginary part. So that wasn't so bad, but let's actually substitute everything in here with the trig form of these complex numbers. So remember, what matters for the trig form is the r value. So I'm going to call this distance from the origin here, the hypotenuse of the triangle, R1. I'm going to call this theta 1. And I'm going to kind of give myself some room here. I'm going to move this down a little bit so we can get some of our identities we need. So remember, A plus BI can be written, that's the Cartesian form. If I want to write it in trig form, we need a relationship between AB and theta and R1. So the trigonometric relationship is that the cosine of theta 1 is equal to A over R1. And by multiplying through by R1, we see that A is equal to R1 cosine of theta 1. The sine of theta 1 equals B over R1, which implies that B is equal to R1 sine theta 1. And all that means is that I could rewrite A plus BI by replacing the A and the B with what I found here respectively, like this. So A is R1 cosine of theta 1, so it's going to be R1 cosine of theta 1 plus B, which is R1 sine theta 1. And of course, you could just factor out let's kind of move this over a little bit. You could factor out the R1 to get R1 cosine theta 1 plus I sine theta 1. Okay, and so similarly, I could replace this C plus DI. If I call this R2 and this theta 2, then I can rewrite this as R2 cosine of theta 2 plus I sine of theta 2. And so the idea is, whereas we just multiplied this times this, right? Let's move the multiplication symbol here, right? That was the multiplication in the Cartesian form. We could also have multiplied those two or represented them in their trig form. So we know that the answer ends up being this here in the rectangular form. Let's just substitute the A, B, C, and D with what we came up with over here. So actually one thing I should do is note that here that C would be R2 cosine of theta 2 using the same trigonometry we did over here, and D would be R2 sine of theta 2. So we're going to use these here right now. We're just going to substitute in to our answer, and then you're going to see that multiplying these two complex numbers in their trig form is going to give you precisely what we see up here. The angles add, the R values multiply. So A, again, remember, is R1 cosine of theta 1. C is R2 cosine of theta 2. Okay, again, just to kind of give myself some room, I'm going to do that. That's AC. B is R1 sine of theta 1. And D is R2 sine of theta 2. And now this is the real part. Notice there's an R1, R2 that can come out. So R1, R2. And what's left is cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. Let's leave that there for now. Let's make it a little smaller for myself. Okay, let's do the same thing over here for the imaginary part. Okay, so remember A again is R1 cosine of theta 1. D is R2 sine of theta 2 plus BC. B is R1 sine of theta 1. And C is R2 cosine of theta 2. Okay, again, an R1, R2. Oh, and we might as well glue the I. I'm going to put the I in the front here. Right, this I is going to go right here. So I can take out an R1, R2, because that's present in both expressions. R1, R2. We'll put the I right there. And what's left is cosine of theta 1, sine of theta 2, plus sine of theta 1, cosine of theta 2. And now here's the final step. So these look kind of messy, but this and this are precisely the identities we see up above. So the one meaning these. So this identity right here is the real part, and the imaginary part is that. So we replace them with what they are. Cosine of theta 1 plus theta 2 plus sine of theta 1 plus theta 2. Okay, of course these can factor out. All right, and so all that means, again, all that is just, that's basically the proof here. The idea is when you're multiplying, so again, remember what we just did was we multiplied this times this, right? We started by doing them in their Cartesian forms, right? But doing them in their trig form shows that the R values multiply, the angles add. And that just means that, so the punchline is if you're multiplying and dividing, I didn't do division here, but it's not too hard to show that either. When you're multiplying and dividing, you want to be in trig form of complex numbers. When you're adding and subtracting, you want to be in Cartesian form.